nitrogen and oxygen. Those are the big three elements that make up us. So it sounds kind of a cosmic kumbaya, 60s kind of thing, but we are all made of stardust. All of the big complex atoms that exist beyond hydrogen in our body had to be formed in the depths of the first or second generations of stars that existed in our universe. So without gravity, without those elements combining hydrogen and helium, and those stars collapsing into supernova, and then you get neutron stars colliding, and that's how you get heavier elements. So literally, all the atoms that make you up at some point had to be formed in stars. It's kind of this cool kind of cosmic thing. So the iron that makes up these springs had to form in the depth of a star that collapsed violently, and then that iron got kicked out, and then our solar system formed, and that iron coalesced, and we ended up with iron ore deposits. So we were able to figure out how to mine and purify, and we can turn it into spring. So on an atomic level, here's your nucleus. Okay, if you remember back, you got protons and you got neutrons, right? Those are all in the nucleus, right? And then you got the electron cloud. Okay, so like on a scale, if you imagine a football stadium being an atom, the nucleus would be like a baseball on the 50-yard line. Everything else in that stadium is where the electrons exist, and that's empty space. So like this table, which seems like it's solid, on an atomic level it's actually empty space. 99% of it is empty space. And you're going, oh, come on, Hurricane, seriously. No, okay, it's not empty space. What you feel is the repulsion of the electron clouds between my knuckles and the table, but on an atomic level, it's empty space. We're mostly empty space, okay? If you're a freshman, that's much higher percentage is empty space, but that's a freshman. Okay, so on an atomic level, when I stretch this, something has to happen to that electron cloud, because these particles get pulled further apart. And then when I let go of it, it has that capacity to go, wow, we don't like this, we want to come back to where we were. It has memory. So something has to sort on an atomic level how those atoms are arranged, and then it remembers it, and then it goes back to that point, okay? So it would be cool if you could build your car out of that same material. It's like, oh, you're an inventor bender. Oh, the car just remembers the shape that it was in, especially if you have a BMW, okay? You want that material to remember, oh, this is just going to bounce back, okay? Insurance companies would love you. Body shops would be out of business because then, oh, you're an inventor bender, oh, it just pops back, and here we go. So what we're going to look at is the force it takes to distort those atoms and make them go. So we're going to look at two things, okay? We're going to look at force and elongation. Now, let me explain what I mean by elongation. When I'm talking about elongation, I'm talking about how far it moves from that equilibrium point, okay? I'm not talking the length of the spring. So let's say we measure the length of the spring, and let's say it's 10 centimeters. So if I pull it down and it stretches to 12 centimeters, my elongation is only going to be 2 centimeters. So what we're going to keep track of isn't the length of the spring. It's how far it moves from that equilibrium point. Okay? It's a key thing. So there's a couple of ways that I could generate this force. I could use my hand, okay? So I could just grab it and I could pull it down. So we have these cool opposable thumbs, okay? Kind of a cool thing, right? And we can grab this and we can pull it down. So as human beings, we can do a lot. You know, we send people to the moon, invented the internet, TikTok, not one of our other inventions, but it's there. So we've done a lot of cool things, but we're not very good at measuring force. So I could come in and say, oh, if I apply a little bit of force, I get an elongation of like 3 centimeters. Okay. So that could be a data point. A little bit of force, elongation of 3 centimeters. I could apply more force, and then I get an elongation of 6 centimeters. Okay, so that can be my second data point. More force, elongation of 6 centimeters. I could apply a lot of force, and then get an elongation of 12. The problem is that's hard to quantify. How do I quantify a lot of force? So, okay, right? If we do that, we get the idea that, not good data. So, like, conveniently, we have a gravitational field, which is a cool thing. So, what we're going to do is we're going to take a mass, and for example, we're going to take 200 grams. So, on the back side of your lab, there's a data table. And so the first thing that we're going to do is that we're going to apply, you got 3 columns, you got a mass, right? And what's the first one's what, 0?
Yeah.
Okay, 0 kilograms. You got 22, you got 24, okay? So here's the deal. One of the things, speaking of gravity, one of the things you've got to get straight in a physics class is the difference between mass and weight. Mass and weight are related, but they're not the same thing. So, and if outside of this room, when you say, hey, what does something weigh? You're going to say, well, it weighs 20 pounds, or I weigh 150 pounds, whatever that is. So, in the common vernacular outside of this class, weight is measured in pounds. In a physics class, we change that up a little bit. Weight is a measure of gravitational force. Okay? So when I say weight, I want that to, you have to realize I'm talking about a force. And any force is measured in newtons. So you all have a handy big dog equation sheet. So let me kind of explain how this is going to play out. You're going to have this big dog equation sheet on every test that you're going to have on all of the homework, doesn't even give it. So on the test, what's going to happen is I'm going to give you like a laminated version of this. So what you're going to do, and this is, it shows you the equations and then explains what they are. Also, over here on that general information, I've got the 3 trig functions listed, which we'll get into trig functions later. How you calculate the area of a circle, and the common prefixes that we use in the metric system. These are the only prefixes we use: kilo, centa, and milli. Okay? You take AP physics and we'll get into like nano and pico and giga and tera and everything like that. We're not going to get into those. These are going to be the big 3 that we use. Now, what you're going to need for this lab, over on this left-hand side, there's a little equation that says Fg equals mg. It's the 5th equation down, okay? That's what we need for this lab. So, when you got this, and it says Fg equals mg, okay? What this is saying is the gravitational force that an object experiences based upon which planet that it's on. So we're on Earth, so we're going to when we calculate Fg, we're going to determine the gravitational attraction that exists between this 200 million mass and this big rock that we're on. Okay? That's what we're going to try and find. It's a simple calculation. When you see this M, remember that's mass. It's not meters. If I wanted meters, I would put like D for distance. This is mass, so I know this is going to be kilograms. And this is my gravitational acceleration. So up here in this box, in the top left corner, you have the value of G on Earth. And unless I tell you this differently, you also assume that you're on Earth. And G on Earth has a value of 9.80 meters per second squared. So what that means is that when I drop something, that's the rate at which it speeds up. So what that means is if I drop something, and I let it fall, if it starts from rest, at the end of 1 second, it's going 9.8 meters per second. If I let it fall for 2 seconds, it's going to gain another 9.8, and it's going to go 19.6. If I let it fall 3 seconds, it's going to go back to 29.4. That's the idea of what acceleration is. It's the rate at which the velocity changes. So on Earth, we have a very, very specific acceleration, 9.8 meters per second squared. And that's the number you will remember. I promise you, you all come back to your 10-year reunion. And I see you and say, hey, what's the acceleration of gravity? 9.8. Okay, everybody remembers that number. Okay, it's 9.8. So, if I want to calculate the gravitational attraction between this 200-gram mass and this entire big rock that we're on, what we're going to do, now I'm going to show you this conversion. I'm not doing this to solar intelligence, but you all have been basically out of school for like 6 months now. I need to make sure everybody's back on the conversion train. So you got 200 grams, because that's what's staying on here. So when you look at this, this says 200 grams. It doesn't say 0.2 kilograms, it says 200 grams. So you got 200 grams, and your prefix over here on your equation sheet says, oh, kilo means 10 to the third, 1,000. So there's 1,000 grams in 1 kilogram. I get 0.2 kilograms. So when you see that 0.2 kilogram, look for the 200 gram mass. Okay? So if I want to figure out what this thing is going to weigh, I'm going to take 0.20 kilograms, and I'm going to multiply that by 9.8 meters per second squared. And check my math, you're going to get 1.96. Now, if I just write 1.96, why is that bad? I don't know what it is. Is it about 96? I don't know what this means. Is it 1.96 squirrels? I got nothing. Okay? But it's a force. So there's 2 ways that you can do force, and it's personal preference. You can look at this and go, oh, that's kilograms meters per second squared. If you're into that, that's cool. If you go, oh, Mr. Burkham, that's a lot of work. Let's talk newtons. Okay, you can put a capital in there. I don't care which one you do, but that's what's going to happen. You have to put something with either kilograms meters per second squared or newtons. So here's what's going to happen. In the lab, you're going to measure the length of this spring, okay? Then you're going to take that spring, and in this case, I'm going to take that 200 gram mass, I'm going to put that on it, okay? And then, at this point, I know exactly 1.96 newtons of force is being applied to that spring. Okay, that's how much force is being pulled down, 1.96 newtons. So I got 0.2 kilograms times 9.8, I got 1.96 newtons. So when this force is applied to it, I know exactly how much force I have. So let's say I measured this length, and now it's like 12 centimeters. So my data point would be 1.96 newtons, so that's how much force I'm exerting. And my elongation would be 2 centimeters. Now, let's make sure everybody's cool with the conversion from centimeters to meters, because the rulers you already used are marked off in centimeters. Do not measure in inches, I will have it come apart. Measure this in centimeters. So, just like there's 100 years in a century, there's 100 centimeters in 1 meter. We can divide that, we get 0.020 meters. So, here would be my data point. I have 0.02 meters. That's my elongation. Again, if this is the length of the spring, it's how far it stretches. And then my other data point would be 1.96 newtons. Okay? So, when you're going to draw a graph, now, on your graph paper, I did use this big sheet graph paper, right? When you do this, on your graphs, there's a couple of things. First off, remember, you're going to be taking a picture of this and sending it to me. Okay, so don't view it as what it looks on the paper. Think one step ahead and go, wow, how is that going to look on a cam scanner when I take a picture of it? And send it to Burkham, he's got to pull it up and grade it as a PDF file. Okay, that's the end game that you want to think. So when you have this, draw like axes inside the paper. don't use the outside axes because that's going to be impossible to show up and you're not going to have very much room and it's going to be really tough for you to see. So we have two variables here. We have force and elongation. Which one is going to be my independent variable? Force or elongation?
Force.
Why?
Because that's what you're like doing to it.
Yeah, I'm controlling how much force is being applied to the spring. So I'm going to have force here, right? And then I'm going to have elongation here. And that force is going to be measured in newtons, and my elongation is going to be measured in meters. So here's the next question. Will this graph start at the point 0, 0? Hey, your thoughts?
Yeah,
Why? It's a good answer. Why?
well, when you aren't putting any force onto it, it's not going to stretch.
Yeah, Mother Nature is raising me on. Mother Nature's going, I'm just showing off, okay? I'm not going to stretch. You want to stretch me, you have to apply a force. So I know this graph is going to start at the point 0, 0, because with no force, I don't have any elongation, okay? So what you're going to do is you're going to come in here, and you're going to plot these points, okay? Now, I'm going to tell you, the hardest part of this graph, or this lab, is kind of deciding what you're going to have on your scale. Now, here's what's going to irritate me to no end. You have this entire sheet of paper. The tree is already dead, okay? Have the tree not died in vain. Don't come in here and draw one little, don't come in here and draw one little graph up there in the corner, okay? You've wasted an entire sheet of paper. My eyes at 54 years old have seen a lot, and they're kind of getting tired. I don't want to have to guess what these numbers are. The purpose of the graph is to visually represent information. And if you can't see what the scales are, then it's a train wreck. So draw this graph big, okay? When you get down to number 3 on the instructions down below, I'm going to tell you, draw a line of best fit. So what you're going to do when drawing that line of best fit, you're going to come in here and you're going to take a ruler. You're not going to do this with just a freehand. And you're going to draw this line so that it splits the difference between the points. Okay? You're going to have some below and you're going to have some above. The next thing that I'm going to tell you in the instructions, and you have to read these instructions, you have to follow what I want you to do. This is why I wrote them out. You're going to find the slope of this best fit line. And one of the things that you're going to have to do first is you're going to have to pick points that are actually on the slope, that are on this line. Okay? You can't use your data points unless your data point actually happens to be on line of best fit. So in the instructions, I tell you, you're going to pick a point. So like maybe I'm going to pick, I don't know, this point up here. So I'm going to come up here and I'm going to say, okay, this is so many newtons and so many meters. And then maybe I'm going to pick this point, and that's going to be so many newtons and so many meters. So you have to do this from my perspective when I go to grade this thing. I don't have the answer to you. All the springs are different. What you choose as your line of best fit is going to be different. I have an idea of what this slope should be, but I don't have an exact answer. So the only thing I can grade is your process. So one of the things I'll tell you in the instructions is to come in here and write down the data points that you're going to use to find the slope of that line. Then on your sheet, you're going to come down here and you're going to find the slope of this line, right? Remember, slope is change in y over change in x. So you're going to have like maybe, I'm just going to make up some numbers, maybe like 5 newtons minus 2 newtons divided by, no, I'm sorry, let's do that up. 0.08 meters minus 0.02 meters divided by 5 newtons minus 2 newtons, okay? Just make up some numbers. So when you're doing this, and again, I can't stress this enough, this is all about the process. I want to see meters minus meters and newtons minus newtons. If you just write 0.08 minus 0.02 and 5 minus 2, I don't know what that means. Okay? And you don't know what it means either. You have loosely written down numbers that don't convey any information. Units have to become an integral part of your thought process right from the beginning. So, when you do this, you're going to get like 0.06 meters divided by 3 newtons. Now, your math teachers will tell you to leave it like this, because they say, oh, this is more precise. In physics, this doesn't really mean anything. Okay? I want a decimal. So when you find your slope, do not leave it as a fraction. Divide this out, I want a decimal. Now, the other thing that you have to begin to realize is that slopes of lines in physics class have physical meaning. So when you do this, and I tell you explicitly in the instructions, I want that written out with the units. So you're going to divide this out, I don't know, let's just say it's 0.033 meters per newton, okay? Whatever that is. So when you get that slope, I want it as a decimal, and then I want these units in meters per newton. Because what this tells me is, hey, for every newton of force that I apply, this is how far it stretches, okay? And you know that because you have the units. If you just see a slope of 0.033, you don't know what that means, okay? Oh, the slope is 0.033. Big deal. I don't know what that means. So show me the calculations. I can only grade your process and make sure that you have the units with us. Now, when you get down to number 4, we're going to have the general equation for the line, y equals mx plus b. Now, we said that it starts at 0, 0. So what's your y-intercept going to be?
0.
0. So don't worry about that. Okay, there is no y-intercept. So with this, on the y-axis, we graph elongation. So on number 4, you're going to say, okay, my elongation is going to equal my slope, which in this case, this isn't going to be slope. I made up this number. Okay, I made up this number. 0.033 meters per newton. And then I'm going to multiply that by what I have on my x value, which is force. So the only thing that's going to change for what you guys have on number 4 is what you have as your slope. But again, this is where the magic happens. If you do dimensional analysis and you go, oh, that elongation has to be meters. I have a slope which has units of meters per newton. I have a force that's in newtons. The newtons cancel out. I get meters. The equation is valid. But if you don't have any units here, and you just have 0.033, then if I multiply newtons by 0.033, I still end up with newtons, and I don't get meters. So that's why it's so important that you go through and you lay this out. Now, because it's been 6 months since I'm guessing you go over your graphs, so let me point out one potential thing with graphs that I don't want you to do, okay? So here's your graph. Don't do this. Here's force. Do that part, okay? But don't come in here and go, okay, I'm going to make that 1 newton, and then I'm going to skip 3, and then I'm going to make that 1.5, and then I'm going to skip 3, and then I'm going to make that 2. You can't do this. You can't let the first 3 divisions be 1 newton, and then skip 3, and then let it be a half, okay? You can't change the scale. If you want to let 3 grids be a half a newton, fine. Then that has to start at a half. That's going to be 1. That's going to be 1.5. So I don't care. And the scales certainly don't have to be the same. Okay? They don't have to be the same numeric. This elongation is going to be really small numbers, like 0.02 or something like this. these are pretty big numbers, because they're going to go from 1 up to 10, okay? So the scales aren't going to be the same, but however you start off this graph, you have to stick with it, okay? And don't change that. So remember, when you're drawing this graph, think it through to the end product. How is this going to look when Burkamp grades it on an iPad as a PDF file? Okay, that's what you want to think through in terms of how you're going to lay this out and how you're going to write it. Okay, I'm done. There's 5 units out, like a group of 2 and a group of 3. There's a whole room back there, social media distance, all that good stuff. If in the course of this lab, if you have a question, ask me, I will tell you. Because it's easier for me to grade labs and papers that are right than papers that are wrong. Okay? So literally, if you're not just like, Burkamp, did I set this up right? Is this going to make you happy? Ask me, I don't. Okay? No worries. Other than that, so on Monday, in class, here's what's going to happen. I want you all to be clear with what's going to happen on Monday. I'm going to go over the dimensional analysis sheet. I'm going to go over this. I'm going to ask the kids that are here, hey, do you guys have any questions? If you guys have a specific question that you want me to go over, join Zoom, type it into the chat, and go, hey, Burkamp needs to go over the gravity question, or whatever that is. And here we go. All right, so by 6 o'clock Monday evening, I want from you guys the dimensional analysis sheet and this lab. And then on Monday, we're going to go over this, and then we'll go from there. So, we're set? Okay. Let's make magic. Did that sound okay?
Give me your thumbs up.
No.